years. He's the professor at the Computer Science and Automation Department here at IISc. He just recently finished his tenure as the chairperson of the department. His research is in the foundations of machine learning, optimizations, and its applications to industry. He's authored numerous award-winning papers in leading journals and conferences in machine learning. He's also a fellow of the Indian Academy of Engineering. Today, he will be talking about his recent work with Ravi, Kannan, and Amit Kumar on the random separating hyperplane theorem and its applications. Without further ado, I'd like to hand it over to James.
Thanks, Drew. This kind introduction, and thanks for this opportunity. This is more of ongoing work. So what is, I guess the paper is up in the archive. I'll have to walk you through four results and see some discussion to be had on that. I think for a standard theory audience, this you may know. I did this separating hyperplane theorem. This in convex geometry is a very interesting, I would say, result, which is the basis of many algorithms in optimization. But what may be a little alien is this, and this is close to my heart. This is the sort of models in which is called unsupervised learning. And what is very key is this part. So these topic models were emerging like at least 20 years ago, and since then it took the world by storm as archiving large collections of unstructured text data. So this part will be contested. What is provable? Right. So hopefully, as we go along, I will try to introduce most of it and then come to the result. Which also means that you will hear more of the second part, a little less of the first part. But we'll see. Unless you are willing to forego lunch. So we have what till an hour or so? Yeah, we'll finish smart. Okay. So first thing, to contextualize this problem, right? What I want to do is to contextualize unsupervised learning and why I think, why is the need for understanding topic models or any risk. Now here is a graph of, it's not very accurate, I believe. Is a timeline of how neural networks have emerged. So first time the perceptron was built in 1957. It was like 10 neurons in a lab. So industrial systems didn't emerge till at least 30 years, and slowly after this, industrial systems started emerging. So now this is an interesting thing on NetTalk where, I guess they wanted to build a network which can understand human speech. It has something like 20,000 neurons. And today you see the quantum jump in industrial models, like 1 billion probably. You would have it, AlexNet, ResNet, and things like that. And it is now said that it will grow progressively, something like, maybe it's already there, we do not know. Now we're not even publishing 100 trillion neurons. So where did all this come from? So this comes from this idea that there are two issues here. So what is AI? Now, this Turing test, that is, if you can mimic a human being, I call it machine intelligence. And that's AI. That's what Turing's definition, and that has been the overarching way the field has evolved. So that means when you copy what human beings do. Very good. How do human beings do? Okay, here is our brain, there's something called neurons, neurons. And the neurons do interesting things, and as a result, I can see, I can act, I can understand songs, music, things like that. But now we are using 100 trillion parameters, right? I mean, of that order. So two things. I'm copying, right? So what the machine doesn't know anything, doesn't understand things. So how does the machine learn? There's large networks. It sends one thing that, look, you give me a set of images, tag it, dog, cat, and I will use this network and try to mimic that tag. This is one. Second, every time I have large number of neurons, I have to find those values for them. That's called training. The more neurons, more messy. Okay. So a sobering thought is, so now doesn't work, right? The human brain has 100 billion connections. It can do many more things. So somewhere we have horribly gone wrong. Which is a good thing. It has come to display. But I think somewhere we have to step back now. We've achieved all these nice things. But I don't think this is the way we can build really intelligent or so-called machines. Just to be case in point, human brain has 100 million connections, right? And so let's elaborate the point a little bit. So first point I already mentioned that you want to copy what you need. Right. So we need label data. Images, dog, cat, all that. Now, sort of to make it interesting, to the Sherlock Holmes code, I would like you to fill up without labels. There is something else there in the actual Sherlock Holmes text. But anyway, but now rule of thumb for linear models. I am doing linear regression, which all of us know very well. You know, it's limited as well. Ax equal to find x exactly, statistically guaranteed, I need 10 times the number of free parameters. So nonlinearity, often our gut feeling is it should be more complicated. Part of that question, make it linear, 100 billion, 100 trillion parameters, complicated. So why is that important? Important means I do not know what I'm doing. I throw something out, something might come out, it may work, may not work, I don't know. And that's what the field is like. Right? So that's one of the important things, right? And also, it's also making things expensive. It's just the same thing is that, see, good engineering should make life easy. You should get good things at cheaper price and things like that. Now, this is driving up the cost of modern day AI systems. How? You need data labelers. So now, if you want, so people say that AI is causing a job crisis, which it is. But new jobs are also emerging. So this is I scrapped this from LinkedIn post. This is exactly happening, and will happen more. This is the line we tie ourselves to. Right. Anyway, so that's one thing. The second most important thing, and that is really worrying, and that is what when I first saw this, it was shaken me to the core, and we are pursuing other research threads on this. So here, on this thing, I've written down names of some networks. Okay? This is an GPT-2 transformer, this and that, right? This is the energy consumption of those networks in kilowatt hour. And this is CO2e is carbon dioxide equivalent of this. So what happens is every time I switch on a light, something like that, right? What is the carbon footprint? How much carbon dioxide I'm burning? So that measurement is in the carbon mix of our electricity supply, right? So maybe when we get the electric supply, that has come from partly from burning coal, partly from hydropower, partly from solar power, the mix of this, right? So the carbon footprint equivalent would be so what is now, as at this point of the time, you do not be really convincing the whatever we do, minimize the carbon dioxide emissions. Okay, but these numbers don't mean anything unless contextualized in certain things. So here's another. Sorry. So this training, right? Now, just to put this in perspective, the air travel New York to San Francisco. This is the CO2e equivalent, right? And look at this. There's one epoch. Now, every time we write a paper, how many epochs they have to write one paper, research paper? So for example, here it is CO2 equivalent is car of a car. And these are all United States numbers. So these cars are not, they're really optimized for environment and things like that, given the current day technology. This is this, right? And look at this number. It's 5 times that. This is the modern NLP language. So every time we are writing papers, ACL and all that, which is good. They say, oh, dude, why did you get this accuracy? Okay, 2 time more iterations. Each iteration is this. So obviously this is becoming unsustainable, and that is why I encourage all of you to read this interesting paper where these numbers I'm taking from. it's a very, very powerful paper, and I was quite shocked to understand this. It's slowly bringing things out of academia is pretty good. That's a different story. Because these are very expensive, costly, and also not very energy friendly. Now, the pioneers, so obviously, Jan LeCun, this is the person who won the Turing Award. In his own words, he's saying that AI revolution will not be supervised. I mean, he's a Frenchman, so he's the take on the French Revolution. So if you say we live in the age of AI revolution, revolution is extremely supervised. Give me data, model, these, that. So there's no understanding the data, and that's what he's saying. So often, for example, we have networks, right? So okay, this network, I've got a very excellent, high efficiency transformer which can identify objects, but it cannot understand music. These are called narrow AI tasks. Human beings can do more things, right? So obviously, so it is, so DNNs of course have revolutionary narrow AI tasks, right? But I mean, that's what this is one of the points I think, not in so many ways, but it's also delivering this thing that we should look beyond supervised learning, right? So now, make it this thing open. Yeah. So now, so fine. That's the thing to do. So basically, then supervised learning is, in some sense, we see this progress. In some sense, is also maybe a little bit well understood. Why? I have a target. Do whatever you want. You have to get the predictions correct. Clear target is here. Unsupervised learning. What's the target? We don't know. What are the formulations? We do not know. So basically, need of the hour is to think about new paradigms. For example, this is where lots of other interesting things are coming. Self-supervised learning, things like that. More things will come. Yeah. But most importantly, we need rigorous formalisms, just like supervised learning case, right, to make it more practical and useful. So that's my pitch for why we should do unsupervised learning. And now, so one can think about it as we said. What is the target for unsupervised learning? I have data. So what should I aim for? What should I do models for? Then what can be the goal? Okay, so now as I said, like for example, in 2 dimensions, suppose I plot some features of say apples and oranges, right? You plot them and say, okay, I give apples and oranges. Now, can you build me a machine which can now give me vector and whether new data point is an apple or an orange? Very simple. I said this is what it is. I no. Draw a line like this. This side of the line is orange. That side of the line is apple. Very good. Now think the first second now. So now, what is given to you now? Features of a fruit, and told apple is an orange, right? Now let's look at the other picture. Same picture. I remove this. Give back the data and say, how do you understand? The same problem now becomes so much more difficult, and you can't come. So basically, when a simple question, right? Like we said, okay, I'll do cluster. The simple question that there's not just pretty open. How many clusters? How many groups? So as you can see, these simple questions we don't have good answers yet. And there's one piece of paper I want to read. It's like the last year. Ravi and Amit trying this question. So this has been consuming us to some extent. But today we'll not talk about this, but we will talk about unsupervised one. So what the target, right? So now unsupervised learning, we have often, when it's a provably, what do you want to prove? One of the things is that suppose data was coming from a model. You do whatever algorithms you want. Can you guarantee you have recovered the true model? That can be one way. Second, this also statisticians will also, and as you see, it's a mix of statistics, it's mainly statistics. Now, the second part is, statisticians will say, yes, yeah, probably we can, maximum likelihood can. But the challenge is that if you look at the results, you say you give infinite number of samples, then I can do. That's not useful. I give you finite number of samples. From that, do whatever you want, give me the model. So that's another thing. How many sample complexity? So these are the questions which are consuming. Okay? So I mean, this is some of the thoughts that sorry. Yeah. So basically, in a nutshell, and this is what today you see, generative AI. Generative AI essentially is understanding generative model. So the discussion. So we'll talk about special class of unsupervised learning models, where there's a generative model of the data. Right? That is, you generate the data. And now I give you samples from that. Can you recover the model? So that is the purpose of this discussion. So one of this thing is, now let's come back to the model in question, which is topic models, right? So topic models, when it was first introduced, it took the world by storm. Mike Jordan was here, I don't know, a few months ago. He was one of those things we did, and they designed this. So essentially, the idea is that they give you a document collection. Let's say you talk about news. Let's say what's happening in news. You just look at like 1 year's of Times 7 news article. What's happening? What news are talking about? How do you pose it? What are the themes? How do you find themes? Now, once you have some themes, then you can say at the archiving level, oh, this is about cricket, this is about sport, this is about this, right? But how do you understand that? Now, throw in the other thing that you don't even know the language. Also, it's not possible somebody to go read all the documents. This is exactly a good case for unsupervised. Give me these documents, whatever you want, and then find themes. So now here, so just to make it more clear, right? So first thing, document, English language. I'm going to something about language, right? Fine. Now I tell you the following question. Suppose you have a document, like a news item, where these words appear. And I ask what the document is about. I think most of us will agree that somebody would say that, this looks like a sport document. Didn't ask what's a noun, word, this, that, didn't ask any of this. This is the thing. So basically, this collection of words is talking about a theme. Okay? Now, and so on and so forth, right? So maybe a group of, so basically not one word, but a group of words occurring is a signal. Maybe this theme is being spoken about. This may not be very useful for conversation, good for archive. So this is about sports. This is about, cooking, things like that. Right? So another question that point was asked is, okay, can you recover this set of themes? We'll make it a little more precise. What is the themes now? But hopefully that gives you the idea that collection of words, if it offers in a document, then that may get you, right? So just to set some notations. So first, convert the data corpus into a matrix. So what we do is, in each row, we use corresponds to a word in the vocabulary. So if the dictionary has D words, these are each row. And what the column is, has the word of, I just said for simplicity's sake, the fraction of words in the document which contains that word. Right? So that means I am throwing away all the grammar. I'm just saying the raw counts. That's what we just saw. Run, inning, hit, season, on. You didn't ask noun, verb, grammar, right? So the relative occurrence, right? That should be good enough symbol. Or you can put any such functions of that. But the key thing is that I am not at this point. Let's take a very simple example, a simple setting that we are not, trying to do more complex things like grammar and things like that, right? Anyway, so I can create for each document and create a big vector, right? Okay. Now. So the generative model. Generative model is as follows. Yes.
The question for Rahul that we can separate topics unsupervised, but can we label the topics in an unsupervised manner?
Can we label the topics in unsupervised manner? See, okay, so we'll come to that in a moment. We'll come to that. Maybe I'll take the question a little later, but remind me of the question. Right? Okay. So another question is, okay, so the question is now, let's put a generative model on top of this. Right? So what is the topic now? So the topic is the distribution of our words. Why is that? Oh, run, inning, hit, season, game. This is occurring more frequently in a document about cricket. So maybe if I put a distribution of the words, the topic cricket will have more. In the topic cricket, these words will have more weightage. Right? In a topic related to cooking, maybe oil, maybe I don't know, calories. This will have more weightage. technology, something like computers, security, software. This will have more weights, right? So basically, now here is something emerging now. So topic is like a distribution over words. Now I make the following assumption. This corpus, just like clustering we do, this corpus is a collection of k topics. Fine. What are these k distributions? So what I do, how do I generate document? Now, generation. Always think of rolling dice. Generation, I take a dice. Let's say there are k topics, k phase dice. I roll the dice. One of the phases show up. With a topic over cricket shows up. Okay. Then I have to generate data from the so-called data from the cricket topic, right? So what you now do is then you pulse the dice which corresponds to cricket. That is how much that's D phase. What is D? The number of words in the vocabulary, as you said. So first I select, I roll the dice, which topic. Then do I do? Oh, cricket topic, dice, and then roll it m times. And what is that number of words in topic? This gives me a generative model of this corpus, right? Okay. Now, so obviously this, so people went through this. There is a standard unsupervised learning paradigm for this EM algorithm, this, that, the elbow thing, which you now see. This was the first time elbow kind of things were discussed. And now, so now, end of the day, there's code running there. So then this is one of the things, slides from David's on the old tutorials. See, we run it on some biology corpus. So for example, you see the topics coming out, something like gene, DNA, genetics, all that, right? So this document will have, those are topics things, right? Now, it also has the power that which word comes from which topic. That also it can mark. So that's being labeled as this yellow. Yellow belongs to this first topic, right? See now, for example, the yellow one and the green one, right? So maybe the yellow topic, we know this is biology, but yellow ones can be something from genomics, whereas brain, neuron, nerve is something from neuroscience. So this was not programmed. It just happened to be discovered these topics. These numbers just came out of the algorithm which is designed. Topic discovery algorithm and things like that, right? So anyway, so maybe it's good to do a detailed thing about this. But the essence of the story is a very powerful thing and very useful and widely used every. Now the question is, see, most of this problems there was now hard to solve, right? Now that led to this area of can you devise A? Can you certify that algorithm provably recovers a true model? Okay. A question you're asking. If not, can you make algorithms which can do that? This have led to an area of this, right? That's where we also do some investigation. So just to set some things in context. So let us say M is a topic matrix. It has D rows. What are the D now? Number of words in the vocabulary. It's K topics. M is D plus K. So if you sum each column, the value will be 21. It's a PMF. Okay, each value is like probability, all that stuff, right? That's it. Now what you do is you now take a k-dimensional vector. That's the rule of the dice, I said. The first dice topics, right? Yeah. Such that they also sum to 1. That's also they also sum to a probability, right? So then you get a new distribution. PMW is a vector. Is also a PMF mixture of this. Now this P is a composite topic. And from this topic, you generate data. And data is what? Data is A. Now, what is the task now? From A, give me M. Okay, this is a setup. Okay. So, obviously, the learning problem. Data is A, we wrote on the matrix. Came from this W in between and all that, right? Finding it. So, obviously, the best fit approach, maximum likelihood approach, right? So A is likelihood. So, like, there's some distributions been put, for example, W is the greatest distribution. So, as you can, maybe one can ask for what the likelihood is, likelihood of the data given the model, and now you can write as a function of M. and you want to maximize that reduce, give me M, which maximizes the length. Right. So first problem is you have to know the distributions and things like that, which is fine. I mean, the algorithms will change the distribution assumptions you make, right? But then what we learned hard way is that, I mean, this is already known. So maximizing the likelihood is easier said than done. Your question.
Asks, can there be multiple topics or a mixture of topics per document?
Yeah, there can be multiple topics in a document. So document can be about, let's say, sports and politics. Suppose some sports person now wants to run for elections, and somebody is reporting. So maybe the sports person went to a cricket stadium and talk about things, but he was announced this election. So it's just sports and politics, right? So that's the thing. Okay, right. So the first thing is that the elaborate model LDA has, and the thing which you wrote down, first of all, maximizing the parameters n. Even give a function is not easy. Just like that. And even more importantly, the L function likelihood itself can be interrupted. So what do we do? So it is more or less focus, right? And all of them has this hand wavy thing that is all asymptotic. That if you get this, if you get infinite number of samples, I give you the sum one. That's not good. Right. So now, so this is what our lesson has been in the field now, something like that. See, the best fit approach is not the good idea. Maximum is best fit approach. So what we do? So we take instead. So basically, the ask is this, right? Right. You know, given data, you give us any algorithm you want. You know, we call them hat, right? Now, if there is a true M from which data was generated, that is so now instead of best fit, you're moving the scope to what is called as a promise problem. There's a promise. There is a M. There's a promise which generates this data, right? I promise you this is what happened. Now, can you now say M minus M hat is pretty close? Okay. So give us any algorithm we want, right? And things like that. So this is so our understanding more on the spirit. So we have doing some things. This is what I wanted to. The latent casing tips is what I want to talk about, but I think I'm way out of time. Half an hour. Okay. So now, after quite a few years, we could put it to a very nice geometric problem, which we call latent casing test problem. And the problem is independent of ignorance. It's a nice convex geometric problem in its own right. So that's what we will take and run with it. So what is it? Right? So if you see this MW, right? MW, right? M is what? Columns. Think like there are vertices of a in D-dimensional space. What is MW doing? Convex combination. What are we talking about? The convex hull. Right? What is data now? Data is not that point in the convex hull. That's distribution. I see data coming from the distribution, right? So this convex hull with this blue colored thing is, yeah.
So it is to find MW or the M matrix.
M matrix. M matrix. Right. Topics. So if this is this columns, right? Sorry, this vertices, right? Extreme points.
Again, multiple W's for which you'll get the same.
So W is not of interest to me. I just need the topics. W is generated for each document, right? So that's it. So the abstract has the problem of W. I don't want to get sidetracked by W, right? Right? You just need to know what topics are. What I'm talking about. What news? Okay. So the idea is that see this. If you want to do this, generate something like this. This yellow thing is that you generate this new point. That's the MW, right? Now we make this geometric argument that sampling from this means what? I'll get a new vector. Now let's assume this vector is close to the mean. No, let's assume that. Right. So maybe the green colored points is what I see. This is like a displacement from the polytope. Full polytope. So now, the learning problem is now, I give you these green colored points, which may be in the syntax, may not be in the syntax. From this, find the pink colored points.
The norm that you're using, does it have an effect?
It does. L2 is easier, 1 is harder.
Yeah, so the infinity.
Infinity norm would be more restrictive, but really what is L2 is most usually, from there are easier bounds. L1 is what we should do, because we're talking about distributions. Okay. So now, okay, so here's the learning gate polytope problem. This is what was introduced in paper, right? So now, here it sets up this problem, right? So this is a problem I think really nothing to do with topic model, nothing to. This is of interest to any point of geometry approach. People who are excited. So I'm given some points. So what is how is that? Just to go with the point setup. Setup is what? There's a polytope. I don't know where it is. What I do is I randomly sample points from it, right? In the polytope. Then I put a bit. Give me the put points. Find the vertices. And this is practical application in terms of talking. This is abstraction, you can think, right? Now we will have to go after this problem. Right? Hopefully it will have and say that, oh, it will have solve topic model. So here it is. So one simple thing to do. This is okay. A simple approach, right? Hey, what is it? You want the vertices. Okay. Well, how do you get the vertices? The convex hull. I get about it, the convex hull. Let's see. The problem is this, right? The hard part is, if you do the convex hull, you will have a large intersection with the volume, which is very good. You'll have approximated the set very well. But is that what I want? I don't want the set from the set well. I want the vertices. And it will be way off. And there is like the challenge. Existing approaches will try to, approximate the volume of the set. This will have a very high intersection of the volume. But it is way off if my guarantee is, okay, in L1 norms term, column. Interest of time, we just say, but the fact of the matter is, the green colored points are essentially, so there's probability of that, right? Now that I've abstracted out and say it's still with the potential. Okay. And now, this, so AI is often called WPI, right? Now from A's, can you find them, right? That is the key.
So what is P? It's like, what are the PIs?
PIs are MW, right? PIs are points, PIs are the, very cool. I take pride in this side. Took me some time. I didn't know this. So yellow, this is the P. Right? And the green color is the A. Right? So this is what it is. Right?
So A is like obtained by sampling from
A is the data. A is what you will see.
that you get by sampling from PI.
Yeah. A is what you will see. Now, so now as you said, there is some, so I think this is just point of volume, not vertices. But I think for this area, I see not very well investigated. High dimensional convex geometry, machine learning. It's just beginning. I feel I think this is just beginning. This is one of the examples, but they have not tackled this kind of problem. So you look at the Brunel's paper, you can look up. It's just a volume. And there's some, of course, some work. For Ravi did some nice work where they want to do. I think Santosh also has some nice work on learning other things. So this is a very nice work who people are excited about, geometry and machine learning. Okay, so now when you set this algorithm, right? So we have to make a few assumptions to make any progress. Not that any polytope you give me I can solve. So first assumption. It's a polytope, right? Now, if the topics are very close, the vertices are very close, I have no hope. They must be well separated. I believe all of you have assumed that. If it's very close, I can't do that. This isn't they're well separated. That means the M1, M2, M3s are very, very far apart. Okay. Next, the perturbation, right? A minus B. So basically, it's like the, so what you can say is like, it's like the variance, if you will. Right? So the total overall variance is small. That kind of thing. A small insights, you have to have some parameterization. Right? And then So it's called spectrally bounded, because in spectral norm, we want to bound this. So it is better than putting infinity norm on each of this, right? So, and then lastly, that is the guarantee, right? So it's a random perturbation, right? So at this point, we don't know, just give random points, what can I do? We have to make further assumption. One further assumption is that we make this so-called proximate point assumption. What is it? We say, okay, then we want 1,000,000 data points. But a small fraction of them, a very, very small fraction of them, lies very close to each of the vertices. We don't know which one. So what is small fraction here? Yeah, this okay, this gamma n. Gamma is a small fraction. Maybe 1,000 data points, maybe 10 data points are lying too close to vertex 1, 10 double next to vertex 2, and so on. A very small fraction. So this is assumption you make. Now, when you make what problem? What makes the problem easy now? And you can guess. See, suppose I get to know this, right? Then I have a goal, right? So that's basically the idea. Now this is bookkeeping. So yeah, now putting all of them together requires a lot of work, and that was the earlier work where you could, as I said, m minus m hat and all that, right? So this is where it is. So obviously, this part, right? They said poly of A, right? Obviously, this thing works well for where K is small compared to P. Yeah. Still, we are in the same setup, so that means there are a lot. We have a lot to go in terms of distance. So one of the things we used is that now let's think about it, just to set some ideas. Think about you had those. Some of you identified those points that are very close to the vertices. Okay. How will you get the vertex? One thing is check a sample average of them. So now the way we went about designing this setup is this. We call subset averaging. So what you do is you take the entire data set, the number gamma you know. You say like, okay, maybe at most 10% of the data, 1% of the data is, so gamma is like 1 by 0.0. So you take gamma in subsets of the data and take sample averages. There are many of them. And now, what is very interesting is that optimizing a linear functional subsets can be easily done. How many such points can be done? The 100 choose the gamma n, right? Sorry, n choose gamma n. That's exponentially many. But still, I can optimize a linear function separately. That's okay. I would like you to think about it how, but that's one of the key. So subsets move, right? Now come back to the rating K political problem. And now I hope I will make that explanation very soon. So what is this thing, right? So now here we keep thinking on this link optimization and things like that. So now then came this interesting thing, right? So the separating hyperplane theorem, what's it? You have a set and you have a point. And what is it? That's the separating hyperplane theorem. If the point is outside the convex set, then draw a line on which side there is the set, the point. And this is the separating hyperplane theorem used everywhere. This is one of the crux of modern algorithms. Yeah. Right. Now, so one thing is that if you see the red phi part, there's a lot of possibilities, and nobody said the same one line. There are many lines are possible. So what can random sampling? The first question. Why random sampling? Well, these are things which makes life easy, algorithmic. I randomly choose points and do things to that extent. So that's the question we asked, right? And now, if you ask that question, right? So what is it? Just to make it very precise, I define direction U. So U dot A is this. This is separating hyperplane theorem. U exists and all that. These will be in a class. Now, since there are many of them, so now can we prove a result like that? Right? You can take a random U and show something like this that, okay, since I'm taking random U, okay, I'm okay to tolerate some error. Error is given like that, right? So here, where K is, let's say, arbitrary set and delta is like just to set the scale of the problem. Delta is like the diameter of this. The question is that if this probability is small, is large, then random you will do. So that's the idea. Another question. Okay. So now this is the random separating hyperplane theorem. Okay. Obviously, as you can see, why is like this? I just copied from the paper. So you can see these equations are as is. So now one can show that suppose use your Gaussians and all that. Now, for example, right now, this factor M, ignore it. Make it D. But D is dimensional. Right. Right.
What is random separating?
Yeah. So let's okay. So yeah. Now the question is, what is U? That's the hyperplane, right? Right. Now can I find a randomly? So now at this point, let's ask the question. Vector randomly. What is this? What is this going to be? Can you characterize? Can characterize two things, right? Characterize the probability of this. Can characterize this error. The dependence have to work out now. That's the thing, right? And on top of it, the idea looks very simple. On top of it, is it useful? The probability is 0. Who cares? Right. So when does it useful? That's the broader question. The answer is question is very simple. I take a random view. What is the probability of getting a separator? Right. Now, so now here is the. This is elaborate statement, but the result is something like this. Okay. Now this M, right? Instead of M, put D. D is the dimension. So root D. Okay. And now, but the kicker is this. So the small k is the number of vertices in the polytope. Here now the result is taken for a polytope, not an arbitrary set. Okay. So now this is the kicker. Right? So it's k to the power 10 by delta square, right? Because delta is the number between 0 and 1. So this is so it does, but the probability is like all that, right? So what is the take home message? First take home message. This is disappointing one. So the probability is not very large, well, right? So first take home message is no. So this thing is very generous. So see, this will not work for when k is very large, small k. Give the 10. They're a bad idea actually. So it will not work for arbitrary sets. To make anything, that is polynomial in k. Hopefully I can use that in an interesting way. When k is small, I think that's fine. So we can leverage some of this, right? But for general convex sets, we don't know how this will go. So yeah, so that's one of the things. But let's come back to our polytope. As we said, we also noted earlier, right? I think it's interesting for talking about this case that k is small compared to d. So that is okay. Here maybe there is some hope, and that's where we are. Right. For general case, of course, more development needs to happen, and most of the bounds I get are maybe an artifact of the proof technique which we are using, assumptions we are making. So there's scope for improvement there as well. Right. But anyway, that's a separate question. Right. So now next thing is so the LKB problem. What is the LKB problem as we discussed earlier? That you give me the green points, find the pink points, and small k is the number of
Is this a back guarantee on the number of samples that are required to get a good separating?
No, it is not a back guarantee. I will not say that. It's like yeah, I don't think it's a back guarantee. It's not a back guarantee. That's number of samples per set. Okay. So now, okay. So now comes this other thing. See, the famous thing I said SDP, the optimization part. So there's also the separating hyperplane, where it comes from, it connects to optimization, oracles, and things like that. So now, so in that spirit, what is very important is to understand approximate optimization. What are the oracles for that? So here it is one approximate optimization oracle, right? So what the oracle does, it takes in a unit vector u, returns a point xu, such that xu will be in the set K. It's slightly outside. BD is the unit ball, right? So epsilon delta K is the diameter, and this, right? So xu will be roughly this. And But U transpose XU is very close to the maximum value of U transpose. This is the maximum. Given a U, what is the maximum of linear function of U transpose by all points Y? Right? So this is what I want. Now this oracle, which will give you very close to that. XU is pretty close to it. Maybe it's not. Right? But the point maybe slightly outside the set as well. How much outside? This is approximate optimization oracle. Some such oracle exists, right? Now using if these things we can now design a paradigm algorithm using this set and maybe this random separating hyperplane. So here is the algorithmic basic premise. So what one can do is to which is called as random probes here in the paper. So you take m random vectors, randomness what we talked about. Okay. Now what did you see in that bound? 1 by k, right? We got I must offset it. Otherwise, don't get meaningful things. So that's the m which offset it, poly of all that stuff, right? Okay. Now you return p. Now, sorry, it's the back notation. The p which I'm using for the slide is the same p. So what you do is you have an optimized oracle, right? The oracle we just talked about. You throw all the UMs you want you to. So what will you get? You will get this corresponding x1 through xn, right? And that's called that set p. Okay. Now now we can show from this p we can create solve the LKP problem, find the vertex, right? Okay. So now how does it do that? And where does so basically what is random separating hyperplane? So what we discussed? It said it is well separated. Okay. So first thing is what you can realize is that you can well separate. So M1 is well separated from M2. So basically that is the point. That's the point. M1 is a point. The k minus 1 remaining points forms also a polytope. So that's the point. M1 does not lie in that set, right? And M1 is quite far, well separated. So that means there's a random separating hyperplane. There is that maybe this exists, right? So similarly, this and that, right? So the idea is now if you pick enough U1 to UMs, if you pick enough of them, there are going to be a reasonable number of U's to be separated. This is the first thing, right? So now putting all of them together is this thing, right? So now M dot L is basically the lth column of M, the lth topic. Now, for each topic, there exists at least one of the U's, provided M is large enough, where this value is maximum. Guaranteed with high probability, right? Or guaranteed with high probability, right? That's right. And now, okay. Now the idea is that if that is there, then if you throw in the x's, now you put the oracle. Now you can also say the corresponding x's will be very close to. Now you see, now the challenge is to keep all the bookkeeping correct, epsilon, deltas, and all that. That's the bookkeeping we have to do, and therein lies the techniques and things like that. But the idea is essentially as simple. Okay, and that's bookkeeping is what makes it challenging, I guess. Okay, and now here, I'm sorry, this is not just didn't get time. I'm sorry, I should have prepared a little more. This is just a copy of the theorem, so you know where to read the theorem. So I think this one to me is the most important theorem, theorem 7.12. So here we already got the P. What is the P? The UMs, optimization oracle linear answer, right? And and what does the previous result tell us? Random separating hyperplane. If M is large enough, in that P, there exists a set of points which are very, very close to ML. And that's the norm you can define, right? So now the thing is, so here's let's see. M is polydial. So now you can see why this has come because of that random separating hyperplane theorem result, right? But if k is very small, it's not that large, I would say. And now even P is M. M is quite larger than much larger than k. But I have to find this k points, right? Now for that again, one can resort to convex optimization, which is called convex algorithm for identifying Q. So Q is a subset of this W. W is a set of answers from this oracle, right? And which will ensure that for every vertex B of k, this B dashed is pretty close to. This is essentially the result. Now, so apart from that's why I titled it differently. You're calling it list learning. So this is there in this paper. So we wanted to flag on one thing. For topic modeling, yes, that's what my interest is. But there are people who are interested in enumerating all the vertices of a polygon. That may have other applications. I don't know much about. But that's a service problem in convex geometry. Now, in this setup, these things also can be used. That's why I say enumerating all the work. That's what we do. Okay. This is also an interesting thing, right? So what is missing in the whole discussion? 2 points. The discussion has to end now. How much time is it? Oh, 5 more. So I must end very soon. So now here, so it is a main theorem. So which is concerned to my LKP problem, right? So the CL, what is CL? CL is the perturbation, noise model, sigma by root n and all that stuff, right? And this is the proximate point assumption, right? And of course, so now the well separatedness is hidden there. Now there is this optimization oracle. You can say that under this optimization oracle, which will, using the algorithms we just mentioned, will return me points which are this far away from the initial vertices, right? This essentially is the core base of the theorem. I'm putting all of them together. So there are 2 points to be noted. So for example, many of you know k-means. Many of you know k-means plus plus. K-means plus plus is an algorithm where you do SVD and then do k-means. It has own benefits. So similarly, a similar rationale and reasoning is also says that instead of doing it on k, what you do is take SVD of the data and run this an algorithm. And that's why this k has all the predictions on that, right? So now the last bit of the puzzle. Where is oracle? This is the key, right? Problem, where is oracle? Oracle is very simple. As I said earlier, actually. Is here the subset smoothing in the so the subset smoothing part can be thought about is providing with oracle. So what it does, what I have to tell you? You have to tell me that you take all the subset smooth data vectors. What are subset smooth vectors? Take all gamma in subsets, average them, give it to me. They're convex half of that, right? That's what it is. Many of them. Now I give you a linear function u. Find me the maximum over that polytope. Now, those of you who know convex geometry, the polytope, the maximum of a convex function, a linear function, will lie at the extreme points. So what do you have to do? Now, all I have to do is take u transpose each data point. One linear scan will give me the n data point. U transpose AI can compute. Sort them, take the maximum, and that's it. That's the simple oracle. And AIs are, and what are AIs? AIs are not. AIs will be outside the set. So that epsilon deltas all that will come, and that is my oracle, which is this kind of what is it? The epsilon. The epsilon guarantee will come from all those other, right? So yeah, so that in a nutshell is what we are doing now. Far from complete. Well, thanks for listening. I think I finished on time. Thank you again. Let's say, yeah, but some round on a question. No, I ditched the question. They are not that don't answer it. What are the question is?
Yeah, so we can separate topics unsupervised, but can we label the topics in an?
No, labeling by definition means somebody else has to intervene. Labeling by definition means that. Right? Somebody else has to tell me. See, I will only know run inning season game. Now, cricket is something you decide. And there are large parts of the world where cricket is still an insect. So any labeling is a human thing. But now the question is now what is the interesting thing about this? That I don't need to even know the language. I just need this occurs. I just need to know these words are cooperating together. And that is the basis for most of these web companies when they want to archive large collections of data. But anyway, this is now pretty mature field, but I think still, the connections which we are finding is, I think it's very rich theory to develop to make it provable and solid and things like that.
So I have a question. Am I audible?
Yes, you are.
I have a question on the topic modeling part, where you say each document is a mixture of topics, right? Each
yes, yeah.
so
Each document.
now there are, for example, in English, and I'm sure this is the case in many other languages, there are a lot of words which are just, in some sense, joining words. So you have prepositions, you have articles.
Right.
Do they belong in a individual topic, or are they?
Yeah, so very good question. This is actually a practical question. Now you do all of this, I try to start running code on this, right? I'll be getting, because most of these words in a document will be of these kinds. Okay. Now, often what information retrieval guys have figured out long enough, these are called stop words. You remove the stop words. Okay, and then do this thing, like from the off, the all that, right? So just throw these things out because that does not signal for us. Then any document. Now, if you have a stop word list like that, throw it, and that's what most people have. Adit, does it answer that?
Yes, thank you.
Right.
Can we apply this algorithm after transformation of the data through some kernel, for example, Gaussian or polynomial?
So okay, so here is a tricky question, right? So now the way we're envisaging is U transpose X. Of course, you're going to write U transpose phi X. But now, where, as I see it, U transpose phi X, I have to know the phi. In kernel methods, often I don't know phi. I have a promise of phi, right? But probably I can think potentially that U transpose phi X. One can even think about U also written as linear combination. So maybe it's possible, but I do not know the probabilistic guarantees the way. For example, a good thing to try would be, what does random separating hyperplane mean there? Right. So how does the guarantee change depending on the kernel? Maybe that's a good thing to try. Yeah, possible. This is possible.
Can a similar analysis be applied on embeddings of a document obtained by a transformer?
Oh, why not? Which means I don't know. But should we try? These are things we should try. You try this thing, right?
Any questions from the audience?
Only question is, when is lunch? No.
So I think we can close the talk. Once again, we'd like to thank the speaker.
Thanks for the opportunity.
Lunch is prepared. Like to give something to us.
Huh? You get also something.
Yeah, you bet.
I see. Ah. Oh. Okay, give me more talks. Thank you. Enjoyed it. Right.